Greetings, I'm Yvonne, staff for Science for the Public, and I welcome you to Contemporary Science Issues and Innovations. Today, we learn about the relationship between the atmosphere and oceans, the sort responsible, for example, for the monsoon season in India. Our guest, Amala Mahadevan, is a senior scientist in physical oceanography at Hole Oceanographic Institution. Dr. Mahadevan is a leading researcher on the physical, chemical, biological relationships that drive the oceans and ocean atmosphere dynamics. Today, she explains how those dynamics in the Bay of Bengal region create the monsoons that deliver fresh water to more than a third of humanity, and how the fresh water, in turn, impacts the ocean structure and circulations. We are very pleased to welcome Amala Mahadevan. Thank you very much for joining us, Dr. Mahadevan. And I'd like to start by asking a question about a very complicated relationship, and we're starting to get acquainted with this more now, but you're the expert on this. How, in general, does that atmosphere and ocean relationship work? What does it include? And like temperature and circulation?
Yeah, so thank you for having me here, Yvonne. The Earth is heated by the sun, and there's incoming radiation, and the Earth absorbs shortwave radiation. Similarly, the oceans absorb shortwave radiation and get warmed up. And the ocean and atmosphere exchange heat, momentum, gases, and moisture or water. And those exchanges are really important for our climate. So 2/3 of the world is covered by the oceans, the Earth is covered by the oceans, and 96% of the water resides in the oceans, or 98%. And so these exchanges are what fuel our weather and our climate. So the oceans are heated, and the oceans give out heat to the atmosphere. And this occurs both in terms of long-wave radiation from the oceans, but importantly, in the evaporation of moisture from the oceans requires energy, because changing the state of water from liquid to moisture requires a lot of energy. And that heat is taken from the ocean surface, and water is converted into water vapor, which is very important in the atmosphere. And when that water vapor rises and condenses to form droplets and clouds, that heat is given up. So that's a form of transferring heat from the oceans into the atmosphere, which is really important for driving convection and rainfall and all of our climate.
Right. And then there's the exchange of CO2 and so forth too. So this is a tight relationship, right?
Yes.
Okay. Yeah. All right. And in the area of South Asia, apparently there are these seasonal forms like monsoons, and we don't really have the same thing, but I will ask you about that. How does that work? What is a monsoon first, I guess?
Yeah, so monsoon really comes from the word mausam, which is an Arabic word which means season or reverse. It comes from the reversal of winds and rainfall patterns. And Asia, South Asia, and East Asia are very strongly affected by this very big phenomenon called the Asian monsoon. And it occurs because of the contrast between the ocean and the landmass, which creates a difference in heating, and difference in temperature creates difference in pressure, and it's like a huge land-sea breeze on a giant scale. That's one interpretation of the monsoon. Another is that the tropics, so if you look at this picture that I have on my computer, we are looking at a satellite image of the Earth, and this is focused on the Indian Ocean, and you see the Pacific to one side.
Yeah. And can you point us to the Indian Ocean?
Yes, so this is the Indian Ocean.
Right, okay.
And the tropical belt is the belt of the Earth which is warmed the most by incoming radiation. And there's something called the intertropical convergence zone. So that's where the air gets warmed and it rises, and you get heavy rainfall and convection. And so this intertropical convergence zone or band is around the equator, and it migrates north and south with the season as the sun migrates to the north and south between the tropics. But over the Indian Ocean, this band, which you see as heavy clouds, it tends to migrate further north than the rest of the world, and so the rest of the Earth. And so that's another interpretation of the monsoons, that the ITCZ is migrating further north, and it's pulled further north because of the Asian landmass.
Okay. So that it's not all even around the Earth.
That's right.
We don't really get the same kind of pattern here. Okay.
Yeah. And the reason is that if you look at the world's oceans, right? So we have three great ocean basins, the Pacific, the Atlantic, and the Indian Ocean. And so if I were to ask you what's different about the Indian Ocean, you'll say that the Atlantic has a northward extent, so it extends northward to the high latitudes of the poles. The Pacific also extends northward to high latitudes. The Indian Ocean is kind of closed off by this huge, big Asian landmass. And so I'll show you this next picture, shows us this huge Asian landmass, and that's what is creating a difference in this part of the world compared to the Americas. So this landmass gets heated, it forms low pressure in the summer, and it pulls in a seasonal wind which lasts for the entire summer season, where winds are coming from the oceans towards this central landmass. In the winter, the opposite happens. The landmass cools off more than the ocean. It becomes a high pressure region, and the winds are reversed, coming off the land and away from the land and towards the ocean.
I see.
So the summer monsoon is called the rainy season because it brings in a lot of winds over the ocean, picks up moisture, and these moisture-laden winds are, also have convection and rainfall, which is very erratic, but it occurs both over the South Asian continent or subcontinent of India, as well as also affecting China. So huge population.
Yes, that is quite interesting. Now we see why that happens there and not in like the regions like North South America, where they sometimes talk about monsoons, but that's another thing. When this happens, it seems like this is a great cause for celebration in that part of the world. And there are two things that, first of all, how much rain are we talking about there, and why is it so valuable? And I have seen reference to even the raindrops are different. They're distinct, like ping pong balls or something. So could you give us a little idea of the monsoon itself?
Yeah, so the monsoon, it starts very abruptly. The onset of the monsoon is a pretty dramatic event if you live in India, and people await it because the dry season is completely dry, very hot in April and May, and then the onset of the monsoon brings this deluge of rain. And it's not continuous over the 3 months. We have these intra-seasonal variability, as you call it, so you have a few days of very heavy rain and downpour and big drops and several centimeters of rain per day, tens of centimeters, big, and then you might get a dry spell. So the monsoon itself is made up of many, many weather systems.
Okay, all right.
And in fact, one of the things is called the intra-seasonal oscillations, where you get wet and dry spells. And usually you'll have several during the summer. And it's trying to predict those wet and dry spells, which is a big challenge, and especially important to countries like India because agriculture is so dependent on the monsoons.
Right. But that's now I can understand readily why you see these pictures of people celebrating, the advent of the monsoon, and they don't. It changes everything, I imagine, in terms of agriculture. You really depend on it and everything else. Yes. Okay. When you have the monsoon, then you have this cascade of fresh water onto the land. But you have pointed out that, well, in turn, this causes a lot of rise of water on land, and that goes into the sea. Is that an issue? Does it change anything in the ocean?
Yeah, so that's something where it's still a topic of research and we are studying. But I can tell you what we think from having looked at the Bay of Bengal. So the Bay of Bengal, that's this region which is to the east of India, is a region which gets some of the heaviest rainfall. So as you know, Bangladesh is to the north of this. Yes. There's a place called Cherrapunji, which has the world record for rainfall. And the Arabian Sea, which is on the west side of India, that's here, in fact, doesn't get quite as much rain. You have some deserts to the west of India. So the big difference between these two basins is that the Bay of Bengal not only gets a lot of rainfall, but the Himalayas are to the north, and so there's a lot of runoff and huge rivers, the Ganges, the Brahmaputra, and the Irrawaddy, which all pour water out into the Bay of Bengal.
Yes.
So the northern Bay of Bengal is getting a lot of fresh water. And that fresh water from the rivers has a little bit of delay because it's sitting on the land and then the runoff.
Okay.
So the summer monsoon is when you have the heaviest rain in June, July, August, and then the heaviest river runoff comes in November or so. And that's when the northern bay sees all this fresh water. Fresher water is lighter than saltier water. So it stays in the surface ocean.
Yeah.
And what's very special about the Bay of Bengal, which we have learned from making many measurements with ships there and putting many instruments out there, is that this density of the upper ocean in the Bay of Bengal is controlled by salinity rather than temperature, which is quite unusual for these latitudes. So most of the world's oceans, there's temperature and salinity that control density. In the Bay of Bengal, salinity controls density. The only other places that that's true is, some river plumes, but the polar oceans, because that's very low temperature. And so the Bay of Bengal is a very unusual tropical ocean where density is controlled by salinity. And what that means is that there's a very strong contrast in density as you go from the surface ocean to the deeper ocean. And that means that there's a layer of ocean on the top that gets well mixed by the wind. And that layer of ocean is called the mixed layer. It's a well-mixed layer. Below that surface layer of the ocean, you have the density increasing with depth. Okay? And in the Bay of Bengal, that mixed layer is very shallow, controlled by salinity. In the Arabian Sea, the mixed layer is much deeper, controlled by temperature. And this is a very nice contrasting system. What we see is that that very shallow surface mixed layer, it doesn't mix. So even when the monsoon starts and the winds blow, what happens is that surface layer remains very thin. And so the Bay of Bengal remains warm through the summer. If you compare it with the Arabian Sea, which is after the onset of the monsoon, water from deep below upwells. So either it gets mixed or it upwells at the coast because of this wind-driven upwelling. And so the surface ocean cools off because of the very strong southwest monsoon winds. In the Bay of Bengal, the surface ocean remains warm, and that's why we think that many of the storm systems during the monsoon, many more of them originate in the Bay of Bengal. You also see many more cyclones in the Bay of Bengal post-monsoon because the Bay of Bengal doesn't cool off because
and
of
that's
this.
The reason for that. Could you tell us a little bit about the cyclones also? So with just to get clear here, with the fresh water has an impact. We're concerned about fresh water with glacial melts now, for example. So that was sort of one of the reasons for asking about that. But that is an important factor depending on where it is happening, right? And so then we have this, but then it has an effect on these weather patterns too, more locally. Tell us what these cyclones are, if you would.
Yeah, so cyclones are weather systems. They are low pressure in the atmosphere, and they are formed typically over the tropical oceans. We also have extratropical cyclones, which are kind of weather systems we see here in North America. But the tropical cyclones, also known as hurricanes or typhoons, are formed over warm oceans. And that happens because the ocean is warm and warm air rises, and it's a low pressure system.
Yes.
And because of the Earth's rotation, these typically are formed away from the equator. They don't happen on the equator. So the Earth's rotation causes air that's flowing in towards the low pressure system to turn, and it starts to turn so that it's in the northern hemisphere cyclonic or anti-clockwise. And this system picks up speed as the air is being warmed by the surface ocean and rising in the middle.
Right.
And so these systems can become very strong and have very strong winds, and they can migrate over the ocean. And really the problem is when they make landfall, they can cause a lot of damage.
Do you see a lot of damage from this? I mean, and it
Yeah.
varies, I guess, year to year. Is that the idea?
That's true. I mean, cyclones are formed all over the tropical oceans.
Yeah.
In the Bay of Bengal, there is a very high population density around the edge of the Bay of Bengal, and many low-lying regions such as Bangladesh. And so it's not that the number of cyclones there are regions with many more cyclones, but this region is very prone to flooding and damage because of the low-lying regions and high population density. And so cyclones are, always a concern. We've gotten better at cyclone warning systems now.
Yes, and I can see immediately why those things can be so hard to predict on, a long-range basis, even a week out or whatever, because it's so complex.
That's right. Yeah, it's the track of the cyclone.
Exactly. But yet, from what you're saying, this really intricate relationship between the atmosphere and the oceans is producing this kind of system, and it is like a system. And with global warming, is that a factor in terms of the monsoon seasons, and is it impacting the monsoon seasons, the cyclones, and so forth?
Yeah, so for the monsoons, I think it's still a topic, very much a topic of research or new research. Mm-hmm. The research suggests that as the oceans warm, you get more evaporation and more convection and more rainfall. And that's true for regions which are already wet. So measurements can show us that wet regions of the Earth are getting wetter, dry regions are getting drier.
Yes.
Yeah. And so there are some suggestions saying that the monsoon could get more intense as a reason of that. There could be some feedback through the freshwater too, that the freshwater creates a thinner surface layer, and so that keeps the ocean warmer and has some feedback on the surface temperature. So globally, surface temperatures on average of the oceans have risen by about 0.7 degrees, but in the northern Indian Ocean, there's been a 1 degree rise in sea surface temperatures. So it's warming a little faster than the global average, but of course it's an average. So there's many.
Right.
And I think there's certainly could be a lot of concern. We think that weather systems are becoming more intense.
That seems to be a trend globally, but where you are used to this kind of thing as a seasonal event, then is that an extra concern now in India, where you depend on the monsoon and at the same time it can't be too severe?
Yeah, so I think the total rainfall from the monsoon doesn't vary that much, and we'd need much longer records to be able to assess whether there's a change. But it's the intermittencies and the intense events that really affect people a lot. So if you have intense events and flooding, and if the periods between the breaks and the active cycles are changed, then that's what changes a lot.
Okay. Before, I want to ask you about some of your other aspects of your work, and I wonder if you could tell us before that, like the CO2 factor now, the carbon factor, because we depend so much on the ocean to absorb there, and if the oceans are changing and all these complex relationships exist, what's your view of that now in terms of will the ocean be able in that region to absorb?
So the oceans, in general, on average, are taking up CO2 from the atmosphere, but not everywhere. In the warmer regions or the equatorial oceans, water upwells from below, and it gets warmed at the surface.
Yes.
And ocean water contains a lot of dissolved inorganic carbon, which is broken up into bicarbonate ion largely. And when that water upwells from deep, it has a lot of this dissolved inorganic carbon. It gets warmed, and that affects the partial pressure of carbon dioxide. So think of a soda water bottle.
Yes.
When you pop it open, that degasses to the atmosphere. And that's because the partial pressure of CO2 in the bottle is higher than the atmosphere, and it comes out of the air. If it were the other way, that you have this creating a soda machine, then you put a
Right.
lot of pressure and water
Right.
gets, and the
Right.
CO2 gets dissolved and goes into the water.
Right.
So the oceans are like that, and the atmosphere. They're trying to equilibrate in their
Yes,
CO2.
yes.
In some places, CO2 is released, like in the equatorial belt.
Yes.
And in the high latitudes, ocean water is cooled. Cold water dissolves more CO2. It's more soluble in cold
Right,
water.
right.
It dissolves, and deep water is formed, and it gets sequestered.
Right.
On average, the oceans are they've taken up, a quarter of anthropogenic CO2 has gone into the oceans. And that's dependent both on the circulation and the heating and warming and
Yes,
upwelling
yes.
and formation of deep water, but it also depends very much on the biology of the phytoplankton. Because these plants, although they have a very small mass
Yes.
compared to land plants, they're turning over very fast. So every few days, the phytoplankton cells are born and they die, and they're produced and they die. And so they produce a lot of, they capture a lot of carbon
Yes.
and put it into particulate form, and they sink out. And
Yeah.
that capture of carbon comes from the dissolved carbon in the seawater. So the dissolved carbon is taken up by the phytoplankton, and some very small fraction of them actually sink
Yes,
deep.
right.
And that's our carbon pump, a biological carbon pump in the ocean.
Yes.
So it's the combination of the biological carbon pump and the circulation, which we call the solubility pump, that helps to sequester carbon.
And if you have a global warming, that can affect the phytoplankton.
Yeah, so this is an
Yeah.
area of ongoing research. There's some studies that suggest that if you warm the surface oceans, the density difference
Yeah.
becomes more, and that will inhibit the upwelling of nutrients and the production of phytoplankton. That's one. Another kind of study is in the, you might say, is in the Arctic. The oceans are becoming ice-free.
Yes.
And but if they're becoming ice-free, then they could be now exposed to light, produce more phytoplankton.
Yes.
So the oceans there's also increase in wind speed in some places.
And
So
current,
and so the higher winds could create, more bringing up of nutrients. So there's
see.
a combination of all these factors, and I think it's a little bit early for us to say. I mean, we know that these processes affect phytoplankton in different ways, but I think the feedbacks are so many between all of these processes and the biology itself
Yeah.
changing, and the acidification of the oceans and changing in the communities of the phytoplankton,
Yes.
that I don't think we know the net of all of these effects could lead.
Right, much appreciated that comment. But this is why I see you do the physics, the chemistry, the biology of the ocean, because there's no way to do a piece of it, really.
That's right, yeah.
The only way to understand it is to understand the complexity of these systems
Yes,
that
I
are
agree.
integrated.
Yes.
Yes, which takes us to some other aspects of your work. This is something I think we're not that familiar with in the general public, that to understand the oceans, you need to go in this direction, these multiple systems and how they work together. And so that must be quite a little challenge. Are there a lot of people, just curiosity here, are there a lot of people that do this?
There are a lot of oceanographers, but I think maybe what I love about it is that the ocean doesn't know the boundaries between physics, chemistry, and biology. Right?
That was my point,
yes,
really,
yeah.
is that you take it on that way, but that it seems as though in much of science, people focus on this piece or that piece. Do you see what I mean? But your take is, no, you got to look at the whole thing.
And I think people realize that. I think it's
because
just,
it's not that it is not that generally well understood. In any case, then I'd like to know more about how you go about studying this extremely complex system.
Yeah. So I want to start by saying I think satellites and the era of satellites has
yes.
been one of the most valuable
I'm sure,
tools
yes.
in pushing our understanding of the oceans and the Earth as a whole, right? Because we now have observations of sea surface temperature, we have observations of sea surface chlorophyll, and these are global observations.
Yeah, and 24/7, right?
Right. And so we can create maps of sea surface temperature and how they evolve in time. We have maps of the rainfall globally. It's mapped out by satellites. We have wind speed over the ocean that's measured by scatterometers. And so we know the wind speed, we know the moisture, we know the rainfall, we know the sea surface temperature, we can measure salinity from space and chlorophyll from space, and the next NASA mission is trying to separate out the different communities of phytoplankton. So as we have soil moisture also from space, we have vegetation. So all of these data sets really help in us understanding the surface, and we're trying to use them to get an understanding of exchange between the ocean and atmosphere. But they're not enough by themselves because they have to be validated, and these are always indirect measures from a satellite. And so in situ measurements are also important. And the oceans are being instrumented in many ways, to a large extent by autonomous instruments. So at this point, there are like thousands of floats in the oceans.
Yes, I think you've been involved in that too.
And the floats are instruments which go up and down in the ocean. So they dive down to 1,000, 2,000 meters, and they come back up because of buoyancy, and they make a measurement as they're coming up. They relay that measurement to satellite. So we have one vertical profile, and then they go and park themselves at depth.
I see.
Because it's safer for them to be at depth. And then they're programmed. After a certain number of days, they do the same thing again. So our oceans are instrumented with these. As always, the measurements are too sparse, but they are building up, and now they used to measure salinity and temperature, and now there's a big program to add biological measurements to those, like oxygen and nutrients and chlorophyll. So we're getting more.
That's amazing, isn't it?
Amazing.
That's really,
that is really amazing.
Okay. So this means you get this huge volume of data, of very different kinds of data, and to put it all together, do you do this with the modeling that you do, for which you're famous too? So how do you do it?
Yes, so we want to integrate these various things, and these data help us provide calibrations, but they also help us test models, but they help us check relationships, and these data are also assimilated into models. So models are run which are for the atmosphere, for the ocean, and now coupled between the atmosphere and the ocean, so that the models themselves are calculating the rates of exchange of momentum and heat and fresh water between the oceans and atmospheres. And so these are called Earth system models, which are coupled, and they are in fact predicting many of our weather systems and
imagine that.
Also climate systems, or the future climate, or even the monsoons. And in fact, the monsoons are one of the very hard to predict phenomena. I mean, they are predicted, but it's the timing of these events in the monsoon that we don't know well in advance.
Well, even, with all that instrumentation, with all the models and everything, nature is still very complicated and one step ahead. But you depend upon those models. But it sounds as though those models can be quite accurate now because of the volume of data and the accuracy of the data as well, right? And so then you can sit down and compute all of this and create an idea of climate change impact and this and that.
It's always hard going in the future. So because you can take all this data at present and put it in a model. So hindcast is easy.
But it's always on changing, isn't it?
But the predictions always have some, uncertainty to them.
And I imagine they could be fairly small changes, like the fresh water or the heat or whatever, and have quite an impact. Is that possible?
So the changes would have an impact on a local system. So it's very hard to predict, a month ahead what the track of a cyclone would be. But if you were to say, predict the overall average rainfall or the average sea surface temperature, we do a fairly good job. But it's the events or the intermittency, the variability is harder to predict.
Right.
And that's what affects us a lot.
And in our last couple of minutes here, this has an impact on how you look at climate change as well. Do you think that this is, well, obviously it's very helpful for understanding climate change and global warming. What would you say on that?
Yeah, so I think, the exchange between the ocean and the atmosphere, I would say, is one of the areas in which we need better understanding, because the number of measurements we have of this, where we actually need instruments which are measuring at the ocean, sitting at the ocean surface, we literally have a few point measurements in the oceans, which are measuring the evaporative flux, the radiative flux, the exchange of momentum. The rest is kind of fitted to these data points. We're taking the satellite measurements and we're inferring what these exchanges are. And we're doing better at those, but we do need more sustained observations. The other part I want to say is that we've, the amount of dollars of research that's spent on studying the North Atlantic compared to the tropical oceans is just, orders of magnitude more. And you would think that the tropical oceans are, of course, very vast in their area, and also
critical.
affect a very large part of the population.
Yes.
But I think we have a relative. So just speaking of the population, I want to show you this graph that I have, where the population is summed up in these blue bars by the longitude. Right?
Yeah.
And so what you can see is that in this region, which is in the circle, is the region that's affected by the monsoons, or the Asian monsoon. You have about 2/5 of the world's population living there. And if you can compare that to, North America and the North Atlantic, you'll see that.
Look how little that is. Right, exactly.
So we need to also think more broadly about understanding the whole global oceans, and I would say that tropical oceans and increasing temperature in the tropics is something that has got relatively little attention. Of course, the poles are also warming very fast, but I think the tropics are where...
This is a really key area. I'm so glad that you brought that up. And we are out of time, and I'm really sorry, because I'd like to pursue that more.
Thank you.
Because, again, that is something we don't really hear about. But we'll take it up at another time. And Dr. Mahadevan, thank you very much for this excellent information. Thank you.
Thank you so much for having me here. Thank you. Pleasure. Thank you.